The Apollo Saturn V dwarfs any craft ever launched into space by the United States. It is 364 feet in height, as tall as a 30-story building, taller than the Statue of Liberty. Fully fueled and ready for launch, this space vehicle will weigh over 3,000 tons, more than a Navy destroyer.
The Apollo 4 mission marked the first operational use of Launch Complex 39, as well as the first launch of the Apollo Saturn V vehicle, which will someday carry 3 Americans to the moon.
Saturn V is 3 huge rocket-powered sections or stages in one vehicle.
The 138-foot-high first stage would provide an initial thrust of 7.5 million pounds to lift the 6,220,000-pound vehicle off the pad to an altitude of approximately 38 miles.
5 giant F-1 rocket engines supply the Saturn first stage with nearly 5 times the power of any booster ever launched by the United States. Apollo 4 will also mark the maiden flight of this 82-foot-high second stage, the Saturn S2.
The second stage was scheduled to burn for 6 1/10 minutes to produce 1 million pounds of thrust.
The 5 J2 rocket engines will use more than 1/3 gallons of liquid hydrogen and liquid oxygen combined in over 6 minutes of second stage boost. They will deliver more than 1 million pounds of thrust. It will be a new expansion of flight testing for the Saturn V third stage, the S4B.
The third stage, after completing 2 orbits, was to ignite a second time to place Apollo into an elliptical orbit with an apogee of 11,400 miles.
An instrument unit built by IBM at the Marshall Space Flight Center in Huntsville, Alabama, is joined to the top of the third stage and furnishes all of the guidance and control signals for the 3 Saturn stages. This is the command module of Apollo spacecraft 17. It has been prepared for the first Saturn V. In place of astronauts, this spacecraft carries a mission control programmer, a series of black boxes which can receive signals and initiate commands for guidance, for propulsion, and for the myriad other tasks which must be performed by spacecraft systems during the complex Apollo 4 test. In all other respects, this will be a complete Apollo spacecraft. The command module is joined to a cylindrical service module, which will furnish rocket power for the spacecraft after it separates from the boosters.
Mr. Glenn Lunny will direct the flight of Apollo 4. Here, he outlines the steps of the mission.
The first and obvious one will be the launch phase from Cape Kennedy. There, the 3 stages of the Saturn V will light in sequence on their way to inserting the spacecraft into an orbit 100 nautical miles above the Earth. During the Earth orbit period, which lasts for about 2 revolutions or 3 hours, both vehicles are relatively quiet and there's no real activity going on in the stages. At the end of that period, however, we prepare the third stage of the Saturn V for its restart. That is, the burn which will simulate the burn we will eventually do to inject the spacecraft on the way to the moon. This burn period occurs at about 3 hours over the United States. It will be followed by a very small burn with the spacecraft rocket engine, the service propulsion engine. This burn will be small, only of about 15 seconds duration. After that time, while we are coasting up to an apogee of about 10,000 nautical miles above the Earth, both vehicles again become relatively quiet. At the end of that coast period, on the way back down, the spacecraft will be prepared again for a large service propulsion engine burn on the order of 4.5 minutes. This large burn will produce conditions, re-entry conditions, which are very similar to the conditions we will encounter when we return from the moon. The entry phase of this flight is also interesting, although we won't monitor it in real time here from the control center. Interesting in that it will be a range of about 2,000 miles and the very high entry conditions which I talked about. The recovery phase will also be of interest to us because that's the proof of the pudding in the flight. and will be conducted in the Pacific about 500 miles northwest of Hawaii.
The 3 vehicle stages underwent extensive checkout inside the vehicle assembly building prior to being erected on a mobile launcher in High Bay Number 1. Apollo 4 was the first flight version Saturn V to be erected in the building. Prior to assembly, the Apollo spacecraft underwent extensive automated checkout and tests in Kennedy's Manned Spacecraft Operations Building. Then it was transported to the assembly building and mated with the launch vehicle. The Apollo spacecraft for this test consisted of operational command and service modules and a boilerplate lunar module. The Apollo Saturn V was subjected to electronic and mechanical checkouts in the high bay. The tests were monitored and controlled in the Launch Control Center adjacent to the vehicle assembly building. At the completion of the VAB checkout, the launch escape system was installed on top of the Apollo spacecraft to complete the configuration.
All of the immense lunar launching facilities at Kennedy Space Center have been readied for their first trial. The largest transporter in the world will move the giant moon rockets to the launch pad.
After a 5-degree climb to the top of the pad, the transporter moved the mobile launcher and the huge rocket into place on the launch site. The mobile service structure was then moved onto the pad. 5 circular platforms on this structure provide access to the spacecraft for final checkout and servicing. A number of significant pre-launch tests were conducted from the Launch Control Center. The countdown demonstration test, a complete dress rehearsal of the 83-hour flight countdown, including fueling all stages of the launch vehicle and spacecraft, began in late September. Several problems were uncovered and corrected during the demonstration count, which required almost 2 weeks to complete. A flight readiness test next included a tie-in with the Manned Spacecraft Center in Houston, from where the Apollo 4 flight was controlled. When pad testing was completed, a launch date for Apollo 4 was set for November 7th. A 6-hour launch window opened at approximately 7 a.m. for an extended number of days. However, minor operational problems delayed the start of the 49-hour terminal countdown until November 6th. Once begun, the countdown progressed smoothly. And on the afternoon of November 8th, the transporter moved the mobile service structure from the pad to its parking area. The service arms, which carry fuel, power, and communications lines to the Apollo Saturn, remained attached to the vehicle until liftoff. Behind the louvered windows of the Launch Control Center, the Kennedy Space Center launch team manned the consoles, recorders, and equipment. The ever-changing display of information confirmed that the countdown was proceeding as planned. As night approached, propellant loading began. Over 1 million gallons of propellant, including 450,000 gallons of liquid oxygen and 300,000 gallons of liquid hydrogen, were pumped into the 3 stages of the Saturn V.
Flight guide. Go. Going to command.
Roger. Flight, we're on internal cooling.
Roger, internal cooling.
S1C locks his pressure at him.
November 9th, 1967. The countdown for the Apollo 4 mission was in its final seconds.
The final hours of countdown had gone off without a hitch. There were no holds other than the ones planned in advance. 4 a.m. Pacific Coast time was liftoff, accompanied by the cheers of a waiting world.
10, 9, ignition sequence start. 5, 4, we have ignition. Ignition detected.
Roger.
All engines are running. We have liftoff. We have liftoff at 7 a.m. Eastern Standard Time.
At liftoff, 7,500,000 pounds of thrust is unleashed from the first stage's 5 immense Rocketdyne engines. The sight of this awesome rocket vehicle, a bright plume of flame fanning out behind it, streaking through the early morning skies on its way to what was to be labeled a near 100% success on this, its maiden voyage, is a picture the world will not soon forget. The test conductor reported that everything looked go, and he was never more right. This was the way it was planned, and this was the way it was going. Straight as an arrow, Apollo 4 kept a course as it thundered on its way into space.
All engines still go. Roger. Flight Fighter, we're receiving data. Trajectory looks Mark 25. Mark 25, Roger. GNC, how are you?
Go flight.
Ecom, go flight. Booster good?
Go at this time.
Status for staging, booster?
Go flight.
Fido?
Go with all sources.
Roger.
Flight RSO green.
Roger, green.
Inboard out.
Inboard out. Tower jet. That's your booster, it looks like.
Throughout the launch phase of the mission, Saturn V, the most complex of all American launch vehicles, performed flawlessly, a tribute to the Marshall Space Flight Center, responsible for its design and construction.
That's the burned-out first stage separating and being jettisoned to fall back into space, its job performed successfully. At this point, the mission now depended on the perfect functioning of the S-2, and it was a picture book performance. The 5 Rocketdyne J2 engines ignited and upped the vehicle's speed to over 15,000 miles per hour. What you're watching now is the separation and jettison of the aft inner stage, recorded on what has to be considered some of the most sensationally beautiful film footage ever taken.
Shown in animation, the second stage performed perfectly for more than 6 minutes. A source of major developmental problems, the stage propelled Apollo 4 to an altitude of more than 100 miles. Like the first stage, the second stage cut off and separated almost exactly on schedule.
After a second stage burn in excess of 6 minutes, the spacecraft was at an altitude of more than 100 miles. The third stage then inserted the remaining 140 tons, the heaviest payload ever launched, into a 118-mile high parking orbit. After coasting for 2 orbits, the third stage reignited to send Apollo into preliminary elliptical orbit.
5 minutes and 25 seconds later, the stage shut down.
How about you? Looks good. Verify guidance. Initiate. Booster, you got a water valve?
Fly water valve open.
Roger.
The third stage and a test model of the spacecraft lunar module fell away. The launch vehicle had done its job.
Roger. Flight to ground track is nominal.
After separating from the third stage, the spacecraft propulsion system was fired to raise the apogee to 11,232 miles.
The spacecraft was oriented so that its heat shield was shaded from the sun, soaking in a temperature 150 to 200 degrees below zero. As Apollo 4 climbed, a camera pointing out the spacecraft window photographed part of what a future Apollo command pilot will see of our planet. Apollo 4 reached 11,232 miles above the Indian Ocean at 5 hours, 46 minutes, 48 seconds after liftoff, and began its descent to Earth.
A second burn of the service propulsion system gave the spacecraft impetus for its 25,000 mile per hour entry into Earth's atmosphere, simulating a return from the moon. This was the most severe test yet of the heat shield, the barrier with a thickness of less than 3 inches that protects the spacecraft and crew from the 5,000 degree temperature of re-entry.
The command module, which would contain the flight crew in a manned mission, was separated, then oriented with its heat shield forward. At about 8 hours, 40 minutes after liftoff, Apollo 4 re-entered the Earth's atmosphere. Temperatures on the heat shield, which was less than 3 inches thick, soon reached 5,000 degrees Fahrenheit. This was 1,000 degrees hotter than the launch pad flame bucket when Apollo 4 lifted off. Yet the temperature inside the command module never exceeded 70 degrees.
Eight hours and 36 minutes after liftoff from the Kennedy Space Center, the Apollo spacecraft landed in the Pacific Ocean within sight of its recovery ship, the aircraft carrier Bennington.
Data analysis showed that it had actually entered somewhat faster than originally anticipated, and the heat shield more than stood up to this strenuous test. While the temperature on its surface exceeded 5,000 degrees Fahrenheit, the interior of the spacecraft never got above 70 degrees.
The flight of Apollo 4 is a successful beginning.
One possible problem area on Apollo 4 was the vibration pattern of the Saturn V during the launch phase. A similar problem in the Gemini program with the Titan rocket had caused much concern until engineering changes had been made. The vibration pattern of Saturn V, determined from post-flight analysis, was programmed into a computer-driven test vehicle. The object, to see if an astronaut could function properly during this stress period. The test subject, Gordon Cooper.
Pitch, 12, and yaw. Back wing left hand, 12, 4.5. Okay, I didn't observe any needle movement on any of the needles. Capcom, that was real good. We got good voice on that. Okay.
Say voice jerky, observe no needle movements.
That's fine. No needle movement, and I was able to have good vision on all of the titles of them.
The results? Man can function to fly the vehicle during the vibration period. There is no problem here.
With all objectives met, Apollo 4, the first flight of America's lunar rocket, was an unqualified success.
The second Apollo Saturn V was undergoing the final phase of ground checkouts preparatory to launch on April 4th, 1968. According to plans, this second flight for the vehicle will largely duplicate the first, and a major objective is to acquire a large fund of additional flight performance data, a necessary step in evaluating Apollo Saturn V's readiness for manned missions.
The flight control team on the ground will be hard at work during 2 orbits as they check the third stage, the spacecraft, and all systems aboard all vehicles. A fully remoted network of ground stations will be exercised for the first time, both for communications from the spacecraft and for the relaying of commands from the Mission Control Center in Houston to a programmer aboard the spacecraft which replaces a crew on this flight. Near the end of the second revolution, when all checks have been satisfactorily completed, the second burn of the third stage engine will be commanded. The engine will ignite and start the stage toward a planned apogee or high point of close to 279,000 miles from the surface of the Earth. After the burn is completed, the third stage will pitch back 180 degrees and the command and service modules will separate from it, then slow down by firing the service propulsion engine in a retrograde attitude. The high point reached by the spacecraft will be about 12,000 miles. The third stage will continue alone into deep space. Near the end of the mission, the service propulsion engine is fired to speed up the spacecraft to a velocity which subjects the command module to lunar return heat loads as it slams into the Earth's atmosphere.
The mission, which was the second for the Apollo Saturn V, was launched from the Kennedy Space Center on April 4th, 1968.
T-minus 15, 14, 13, 12, 11, 10, 9. We have ignition sequence start. 6, 5, 4, 3, 2, 1, 0. We have commits. We have liftoff. Liftoff at 7 a.m. Eastern Standard Time. 5 seconds into the flight, we're looking good. We have cleared the tower. We have
understand tower clearance. Houston Center assumes control. Pitch and roll program started. Our vehicle going now to an azimuth heading of 72 degrees. All 5 F1 engines firing, looking good. Given a green light at this time from range safety. Roll program is completed now. Pitch profile still in progress. 40 seconds. Mark 45 seconds. Our vehicle well beyond the beach now. Our IP impact point moving out well over water as desired. Mark 56 seconds. Our cabin pressure is relieving, coming down now from a pad base, 16 pounds per square inch. Looking good. Mark 1 minute, 10 seconds coming up on our period of maximum aerodynamic pressure on the vehicle. Still looking good. Mark 1 minute, 25 seconds. Pass through max Q. Still looking good. Now 10 nautical miles in altitude, heading out beyond the Earth's atmosphere. We're on our way. Mark 1 minute, 45 seconds. 14 nautical miles in altitude, 12 nautical miles downrange. Velocity at this time, 4,600 feet per second and accelerating. Mark 2 minutes, Flight Director Cliff Charlesworth now polling members of his flight control team as to our status for staging, and we're standing by. Center engine has shut down. Our 4 outboard engines have shut down. Booster engineer reports ignition on our second stage. Our first stage will be falling away shortly. Now it's day's work done. Again, the greatest weightlifting effort ever. Mark 2 minutes, 50 seconds, 40 nautical miles in altitude, 70 nautical miles downrange. Our interstage has separated this crucial timeline event right on schedule.
There was an unacceptably high level of an up and down vibration, or oscillation, along the vehicle's length. This occurred late in the first stage burn. Several square feet of material separated from the structural shroud enclosing the lunar module. 2 of the second stage's 5 J2 engines shut down early, and the third stage's single J2 failed to restart for a planned second burn. Nonetheless, all separations were normal. Other systems functioned properly, both for the launch vehicle and the spacecraft. Some of the most valuable photographs for the Earth Resources Survey program were recorded during the second orbit by a camera pointed out a window in the command module.
After 10 hours in space, the command module was rammed back into the Earth's atmosphere, simulating a lunar return. Another milestone in preparing for moon missions.
Finally, in the Pacific Ocean, the command module was recovered in excellent condition. Throughout the mission, a flight crew would have been safe in spite of anomalous conditions. Immediately, attention turned to investigating and solving the problems. During the unmanned Saturn V flight, Apollo 6, several technical problems developed. The 2 major problems were the excessive vertical oscillations, or POGO effect, that occurred during the first stage flight, and separation of several pieces of material from the lunar module adapter area, which was apparently caused by the severe oscillations. After extensive data reduction and study by NASA and contractor personnel, one of several possible solutions for the POGO problem was selected. The solution consists of adding helium to an existing cavity in the liquid oxygen pre-valves of the first stage propulsion system. This forms a shock absorber, which changes the natural vibrations of the propulsion system to about 2 cycles per second. Comprehensive static firings of a single F1 engine were conducted both at the Marshall Center and the Edwards Flight Research Center, California, to obtain data to verify the validity of this solution. Engineering analysis of test data revealed that the fix was completely effective. In early August, a final and full-scale test of the POGO solution was conducted at the Mississippi Test Facility. The first stage for the 6th Saturn V vehicle was fitted with accumulators and fired for full duration. The analysis of data from the firing indicated that the POGO problem is solved. The oscillation levels for the upcoming Apollo 8 flight will not exceed those of the first unmanned Saturn V, which made a perfect flight last November. The fix has already been applied to the first stage for Apollo 8, the first manned Saturn V mission. All other Saturn V first stages are currently being modified.